Benim gece ve gündüz tamamen karışık şu anda. O yüzden uğultudan da böyle şey oluyorum. Sınavla ilgili sormak istediğiniz bir şey var mı diye hemen sorarak başlayayım. Şükrü'nün okumaya başlaması gerekiyor önce. Ama o da hastaymış anladığım kadarıyla. Right then, we may start with our discussion about discrete time Fourier transform. If you may remember, this is the topic that we were covering. We have seen quite a few examples about this discrete time Fourier transform, but we didn't start seeing the properties of the discrete time Fourier transform. And as you may remember, in solving questions, what we usually do is to take a look at the properties of the transformation, and using those properties and using the well-known transformations by associating with them, we solve questions. That's how we do things. The properties, therefore, let's start. The fundamental property of the discrete time Fourier transform that you have to always keep in your minds is that this one is periodic, 2 pi periodic. This is a very pronounced property, and you have to check your results to make sure that the Fourier transform that you come up with becomes 2 pi periodic. And what does that mean? It means x of e to the j omega, the Fourier transform, is equal to or must be equal to e to the j in parentheses omega plus k times 2 pi, depending on an integer k. So this is something that you have to always keep in your minds. Starting with this property, let's consider a low-pass filter h of e to the j omega in discrete time, a discrete time low-pass filter. What does a low-pass filter look like? It looks like this, with a cutoff frequency omega c. So from minus omega c to omega c, this is an ideal low-pass filter, right? Normal low-pass filter. But of course, for a low-pass filter in discrete time on the axis of omega, this must be 2 pi periodic. So we must have replicas like this and periodically extending to the left and to the right like this. So how do you come up with a high-pass filter then? How can you draw a high-pass filter? So this is a low-pass filter. And in this low-pass filter, the critical situation is the situation that appears at integer multiples of 2 pi, including 0 times 2 pi. But this is reasonable. This makes sense. This one is a little bit confusing. For a proper low-pass filter, we must have the frequency of pi, and minus pi, of course, to have nothing. Because this is the highest frequency that we have. So how do we obtain a high-pass filter then? What is a methodology to come up with a high-pass filter? Or can you draw a high-pass filter? A new h of, let's call it g of e to the j omega. Let's give a different name to that. On the axis of omega, what should it look like? It should look like similar shapes, but they must appear at odd multiples of pi, like this. So if this is 2 pi and this is pi, around pi we must have a passing region like this. And there must be nothing at 0 and integer multiples of 2 pi. But around 3 pi we must have something. Similarly around minus 3 pi. Now, can you mention the similarity between the two? Or how can you generate one of them? Let's call G from H. Yeah, just shifting by a factor of pi. So G of e to the j omega could easily be called H of e to the j omega minus pi or plus pi, it doesn't matter. Now what is e to the j omega minus pi? It is equal to e to the j omega e to the minus j pi. And what is this? No? Minus 1. So, interestingly, h of e to the j omega minus pi, or let me repeat it here, could also be expressed as h of minus e to the j omega. That's very strange. By putting a minus sign here, I make things to be pi shifted. And that minus sign, if you consider e to the j omega n, what happens to this inside such a process? Because we know that in the expression of the Fourier transform, this is what we have, e to the minus j omega n, in fact. But let's consider it like e to the j omega n. What happens to e to the j omega n when we do it like this, e to the j omega minus pi n? When this turns into this, what happens? It becomes e to the j omega times e to the minus j pi, e to the j omega n times e to the minus j pi n. It becomes like this, okay? And e to the minus j pi n is what? What was e to the minus j pi? It was minus 1. So e to the minus j pi to the power n is minus 1 to the power n. Minus 1 to the power n times e to the j omega n. So every term, if you remember the Fourier transform expression, in the Fourier transform expression we had a summation x of n e to the minus j omega n. Every x of n will be multiplied by not e to the minus j omega n, but something like this, minus 1 to the n times e to the minus j omega n. What I mean is this. In this summation, x of n e to the minus j omega n, which is the Fourier transform, transforms into x of n times 1 to the power n times e to the minus j omega n by pi shifting. By making a shift of pi from a low pass to a high pass, this is what we do. And it gives us a hint that the high pass version of your signal is obtained from the low pass signal by multiplying your signal with minus 1 to the power n. That's how you should do it. So the high pass filter or high pass version of x is equal to low pass version of x times minus 1 to the power n. What is a minus 1 to the power n? It is either plus 1 or minus 1, alternating. So that's what you do. You, for example, take a low frequency looking signal like this, smoothly varying low frequency, and you make it alternating in magnitude, plus and minus alternating. You keep one sample, you make negative of the second sample, then you make positive of the third sample, again you make negative, again positive, again negative. So this is the process to come up with a high pass signal from a low pass signal by alternating their signs. Since it is the most frequently changing version of your signal, this one is pi shifted version of this one. That's how you do it. So the first property therefore gives us an idea, a hint about the shape of the Fourier transform. If you have a shape of the Fourier transform which is arbitrary but 2 pi periodic, of course, and if you want to come up with a pi shifted version, let's say a high pass version of the low pass signal, original low pass signal, what you really do is in the time domain you take it and you alternate their signs. Okay, so this is the method to come up with pi shifting or low pass to high pass and equivalently high pass to low pass variation. From this high pass, what is the method to obtain a low pass signal? You again alternate their signs. You say this times 1 is itself. Then the second 1 times minus 1 is that over there. Then this times itself is there. This 1 times minus 1 is there. So from here to here it's another pi shift as well. Alternating again and again to perform pi shifting. Now let's talk about another property. The next property that we'll talk about is differencing. It's like taking the derivative, differentiating in time. Do you remember what was happening when you take the derivative of your signal? If the Fourier transform of this one is x of j omega, what was the Fourier transform of the derivative signal? No, it was j omega times x of j omega in continuous time, of course. This is what we have. Now in discrete time we don't have a differentiation, of course. We have only differencing, and things are a lot easier than differentiating, because in differentiation it's quite awkward to see why this kind of an effect by multiplication with the j omega will make a derivative. However, the difference x prime of n in discrete time is quite simply xn minus xn minus 1, which is the first difference. So what is the Fourier transform of x prime? That is capital X prime of e to the j omega, the discrete time Fourier transform. It's equal to the discrete time Fourier transform of this one. It's capital X of e to the j omega. And the other one is just a shift by 1. And a shift by 1 is e to the minus j omega, or e to the j omega times minus 1, in other words. X e to the j omega. Now when we combine this in a parenthesis of x of e to the j omega, it becomes 1 minus e to the minus j omega times capital X of e to the j omega. Now with respect to the top thing, what can we say about the differencing effect? The differencing effect is nothing but multiplication with this 1 minus e to the minus j omega. It's not multiplication with j omega anymore. Previously it was simply multiplied by j omega. Now it is multiplied by 1 minus e to the minus j omega. Well, in fact, if you come up with a j omega multiplication, you must be worried a lot. Because when you multiply with j omega, your Fourier transform, suppose this is already 2 pi periodic because it's a discrete time Fourier transform. When you multiply it 2 pi periodic signal by j omega, it's no longer 2 pi periodic. Okay, it changes. That this multiplication will violate the 2 pi periodicity. However, when you multiply a 2 pi periodic signal with another complex exponential form like this, then it is still 2 pi periodic, and therefore everything is consistent with our observations. Everything must be 2 pi periodic. But is it similar to a multiplication with a j omega is another question. It looks very different, right? For the first, we are multiplying by j omega. For the second, we are multiplying by 1 minus e to the minus j omega. They look very, very different. How come their effect is, in a sense, or somewhat similar? Why is it the case? I'm not going into the details of that. I won't go into the details of that, but I will just give a brief motivation about how come they are sort of similar to each other, j omega and 1 minus e to the j omega. Is this similar to 1 minus e to the minus j omega? A full proof of their similarity in any sense is rather difficult. So the motivation that I will propose is something like this. Let's take the magnitude of these things. What is the magnitude of j omega? It is omega, but the absolute value of omega. What is the magnitude of 1 minus e to the minus j omega? Now that's a little bit more involved. It's the magnitude of 1 minus cosine omega plus j sine omega. There is a minus sign, of course, but it's there is another extra minus, so it becomes plus. So how do we find the magnitude of this? The magnitude is, this is the real part and this is the imaginary part. The real part square, 1 minus cosine omega square plus sine omega square, and you take the square root. When you take the square of this, it becomes cosine square omega plus 1 minus 2 cosine omega. Okay, and from here we have another sine square omega. And this cosine square plus sine square is 1, so we have 2 minus 2 cosine omega. All right, now what is that? And the square root of that. The shape of this thing, when we plot, looks like this. Roughly, this is the plot of this expression. And what is the plot of absolute value of omega? I should plot at the same axis. So what's the absolute value of omega? It's this. So this is absolute value of omega. This is the absolute value of, or the magnitude of 1 minus e to the minus j omega. Now this similarity between these two appears only for relatively low frequencies here. And notice the V shape that you have here. That V shape is the discriminator operator in the Fourier transform domain, in the frequency domain. And this is the exact V shape, of course. This is the precise differentiation. This is differencing, first order difference approximation, and that's how these two are similar. So if your system, just plot your system in magnitude, okay, in any example, just try to draw it. If you cannot draw it, use the Fourier transform tools or functions in MATLAB. Just do it there and take a look at your function. If your function somehow has this kind of a property in between, then that is a differencing operator. Okay, it's a differencing way of acting on your signal. And another further property of the differencing operator is that it doesn't pass the DC. The DC is zero frequency, it's here, and this filter is not passing anything because the magnitude is zero. Zero here and zero here. When you take the derivative, you get rid of the DC. You lose it, in other words. Okay? That's a property that we must have. Then if this is the derivative operator here that we have, or continued with examples over there, then what can we say about the integration? And in discrete time, the integration is an accumulation, a summation, in other words. So differencing is this. Integration is, for our case, accumulation. And this accumulator is this y of n, the accumulator output is equal to k from minus infinity to n, the summation of all the signals up to the instance of n, x of k. This is our accumulator, which is the inverse system of the difference operator that we have seen over there. And therefore, the Fourier transform of this, which is y of e to the j omega, is equal to 1 over 1 minus e to the minus j omega times x of e to the j omega. Sort of. This portion, it's understandable. It's like saying 1 over j omega for the integral property in continuous time. But do you remember that it was not the only thing that we had? We had some extra coefficients here. We must incorporate that plus c, which is the DC coefficient that we lose while differentiating. Unfortunately, it's also here, but it's not a single component of DC anymore. Because if you insert an impulse, a sample in the DC, since everything must be 2 pi periodic, you must replicate those impulses at 2 pi, 4 pi, 6 pi, minus 2 pi, minus 4 pi, etc. So it must be in the form of a summation. It's not a single term that I will put here, therefore. It's in the form of a summation. And that is plus pi times x at dc e to the j0, omega is equal to 0, and I will put, first let me put the impulse, delta omega. So it's the DC impulse, which is the DC value that we lose by multiplying with a 0 at omega is equal to 0. But it must repeat itself, so the repetition is by a summation, as your friend has already suggested, k from minus infinity to infinity, omega minus k times 2 pi. So it's a little bit complicated, as you see. Rather long expression, but it's simple. It's just pi times the DC value in the form of an impulse in the center, in the DC way, just like the continuous time integral example. But we must replicate those impulses at integer multiples of 2 pi by making a summation. And by the way, this term is a little bit awkward looking as well, because in books you may not find it like this. Capital X of e to the j 0. I'm explicitly writing it to be more explaining, meaningful. Omega is equal to 0, e to the j 0. It's x of e to the j omega at omega is equal to 0, in other words. But in some of the books you may find it very interestingly in another form like this. Because that's what it is. E to the j 0 is e to the 0, and something to the 0 is 1. So it is capital X of 1. But when you see it like this, or if I explain it without writing like this, if I only write it like this, it's very difficult to understand that it corresponds to omega is equal to 0. But it is. So don't get confused when you see capital X of 1 in discrete time Fourier transform expressions. It means it corresponds to, in other words, omega is equal to 0. You expect, I mean I do at least, something like this, x of 0, right? This is omega is equal to 0, the Fourier transform at omega is equal to 0, but it's not. It is this, x of 1, because everything is in the exponent, strangely. Okay. Now let's see another example, another property in fact. The new property is upsampling. What do we mean by upsampling? Upsampling is like this. You have, let's say, a discrete time signal like this. 0, 1, 2, 3, and all the others are 0, let's assume. This is your discrete time signal. Let's call it x of n. We will notate the upsampling like this with a subscript of an integer value. Let's call it 2, x sub 2 of n. It means I am trying to upsample this signal by a factor of 2. It's like stretching, making a longer signal from this. But it is discrete time. How can you make a discrete time signal longer? The separation between these two is an integer 1. What am I gonna do? I mean, how can I make this signal longer? If you have old rubbers, okay, a little bit aged, because if you have a fresh rubber, you may stretch it and it will stretch, and you will notice nothing. It becomes a little bit thinner perhaps, but it stretches. But if you ever see an old rubber, if you try to stretch it, you will see that some parts will be separated, cracked. So this one will also be cracked in a sense. In upsampling, it must be, and the upsampling factors must always be integers. We cannot make this signal 1.5 times longer. We can't do that. We can make it only 2 times longer, or 3 times, or 4 times, integer times. For example, if we make it twice longer, then we keep the signal at 0. Then we insert an extra 0 in between. We crack. Then, so this is at 0, this is at 1. We insert this signal, which was previously at 1, here. Then we put a 0. And then this one, which was previously at 2, we put it at 4. And then another 0. This one, which was previously at 3, we put it at 6. And we don't have anything else. So this is it. This is the signal, which is sort of a stretched version of the top one. So how are we doing upsampling then? We are inserting zeros in between. This is an upsampling with a factor 2. which inserts 1, 0 between every previous sample. If we upsample by a factor of 3, how are we going to do that? We will insert 2 zeros in between every sample. So it will be 3 times longer. This is twice longer than this one, by the way. Okay, that's what it is. So this is upsampling by explanation. But of course, it's not upsampling that we are interested in. We are interested in the transform of this thing. And how can we relate the Fourier transform of this to the Fourier transform of the original signal? What is the relation between the two? And from there, it may be beneficial to start by what was happening in continuous time. Do you remember the Fourier transform of a time-scaled version signal? This is, or it was, one of the things that we have already seen, and it was this. The relation between the Fourier transform and the time-scaled version was like this. So when you scale the time by a, if you multiply in by a in t, then you have to divide omega by a. That was an expected behavior, right? If you squeeze your signal, it means you are expanding your Fourier transform. If you're expanding your signal, you are squeezing your Fourier transform. So if you multiply t by a, you have to divide omega by a. Inverse relation. This kind of an inverse relation is still valid in the discrete time Fourier transform case as well. This one, for example, will have the Fourier transform. If the Fourier transform of the original is x of e to the j omega, then the Fourier transform of this one will be x of what? Are we dividing are we dividing n by 2, or are we multiplying n by 2? This x sub 2 of n is what? In other words, can we express this as this using a piecewise expression? Using that piecewise expression, in fact, it is this. Uh, 2k, an even signal, in other words, 0 else. So the upsampled version is that. And over there, what I mean is this. For example, x sub 2 of n at n is equal to 2 is equal to x of 1. So this 2 is divided by 2 and we have obtained 1. Or this 4 is divided by 2 and it actually corresponds to the original x of 2 here. So x sub 2 of n is x of n over 2 in general. So we are dividing by 2. And if we are dividing by, if we are dividing our time, then we must multiply our frequency. E to the j 2 omega. That's it.
2 times x.
What do you mean?
Mesela biz onu 2 ile çarptığımız zaman orada bir bölü a yapıyor ya. Onun bir bölü a'dan
no, it's like this. N over 2 in time will have a relation as 2 times omega in the frequency. A times t in time will make omega over a, and here it is 1 over 2 times n, therefore it is omega over 1 over 2, which is 2 omega. We are dividing our time by 2, so we must multiply our frequency by 2. And in that case, it means the Fourier transform of this one is capital X of e to the j 2 omega. And what does it look like? It looks like this. If you have an x of n, which has a Fourier transform of x of e to the j omega, let's give a shape, an arbitrary shape to this x of e to the j omega. Let's assume that it's low pass without any loss of generality. Like this. Notice that it is 2 pi periodic. Okay, so this is x of e to the j omega. Now what does x of e to the j 2 omega look like with respect to this original shape? What happens to this shape? Yes, it must be squeezed because we are expanding in time. Therefore, this thing must squeeze in frequency. So it must be narrower. How many times narrower? Twice narrower. I'll try to draw it here. So this will be narrower around 0. So let's assume that it was the cutoff is A, so we must have A over 2 as the cutoff frequency, the new cutoff frequency. What happens to this triangle? That triangle must come back to pi now. So around pi, I must have the replica of this, but narrower, of course. And then, do I have another triangle at 2 pi? Yes, the triangle around 2 pi will be the narrowed version replica of the previously 4 pi. 4 pi comes to 2 pi. 6 pi will come to 3 pi. 8 pi will come to 4 pi, etc. So more or less this is the situation that we have. Now the first question that you must ask yourselves, is this 2 pi periodic? Yes, it is. It is even more than that. It is pi periodic now, but anything which is pi periodic is automatically 2 pi periodic. But there is a fundamental difference between the behavior of this one as opposed to the behavior of the previous one. The behavior of the previous one was a low pass signal. It was around 0, 2 pi, 4 pi, etc. And around pi we had nothing. But the new one, there's a problem. It changed. Now we have some energy in around pi and around 3 pi, around 5 pi, odd multiples of pi also exist now. What does that mean? It means that my new Fourier transform does not correspond to a low pass signal anymore. It becomes somehow a high pass signal. Low pass and high pass components. Now can you see why that could be the case by looking at this shape as opposed to the shape at the top? The shape at the top was smoothly varying, let's assume, a low pass signal. Now this one is not very smoothly varying. It is non-zero, zero, non-zero, zero, non-zero, zero, non-zero, zero. So that variation is quite rapid. In fact, that is the maximum frequency that you may have. A non-zero, zero, non-zero, zero. It's like positive, negative, kind of a zigzag variation, which corresponds to the highest frequency, that is pi. That's why we have some pi component, high frequency component here, as opposed to the non-existing high frequency component here. This is purely low pass. This one is high pass. And the Fourier transform of this one is here. And the Fourier transform of this one is here. Okay. So when you do upsampling, without thinking of anything else, we can write it like this. It doesn't have to be an upsampling, sorry, an upsampling by a factor of 2 only. It may be an upsampling by 3, 4, etc. Let's just call it k. This is an upsampling by a factor of k, and the Fourier transform of this upsampled signal is x of e to the what? J times k times omega. That's it. If it is 2, it is e to the j2 omega. If it is k, that is e to the jk omega. Simple. So upsampling is quite easy in Fourier transformation. You can do it. And the way to draw it is very simple as well. You have to just squeeze your Fourier transform with an integer fraction. You must squeeze it by 2, by 3, by 4, etc. And it will always be, of course, 2 pi periodic. In some cases, there will be something around pi. In some other cases, there won't be, perhaps. Just you need to squeeze your shape. That's it. Integer fold squeezing. However, when we come to downsampling, now I will only tell you what downsampling is, and I'm not going to the Fourier transform of that for a reason. If your signal is like this, how can you squeeze your signal? Stretching twice is okay. You insert zeros in between. Can you squeeze this signal? No. The separation, no, you can't do that. The separation between every signal is and must be 1. It can't be 0.5 because that's the definition of a discrete time signal. So how are we going to squeeze this signal? Well, we don't. What we call is downsampling, and it's a little bit different than squeezing. What we do is we get rid of every other sample, every second sample. So we take this, and then we omit this, and we take this. Then we omit this, and we take this. And then we omit this, and we take this. And this is what we get. A shorter signal, but we are losing information. So there is information loss in downsampling. But the formula here is easier in time domain. This downsampling, I don't know if we have a relation or a way of representing. If this is x of n and this is y of n, then y of n is nothing but x of 2n. That's a downsampling by a factor of 2, by the way, that I'm illustrating. It could be downsampling by a factor of k as well. Then you eliminate, if it is downsampling by a factor of 3, for example, then you eliminate 2 of them and then take this one. Lose 2 other one and then take this one, etc. You go on like that. This is downsampling by a factor of 2. But what is the Fourier transform? Now the Fourier transform is problematic because, as you see, in terms of analogy, you are squeezing in time. Therefore, what do you need to do in Fourier domain? You have to expand in Fourier domain, right? When you expand it twice, assume that we are doing downsampling by a factor of 2. So that is y of n. What is the Fourier transform of y of n? The straightforward answer is expand this by a factor of 2. When we expand this by a factor of 2, what will the shape look like? It will be a wider triangle here. And this 2 pi will go to 4 pi as a wider triangle here, etc. So it is 0. This is 4 pi. Now, Is this 2 pi periodic? No, it's not. Which means this can't be the Fourier transform. So the Fourier transform is not simply, what was the Fourier transform for the upsampling? It was e to the j k times omega. So the Fourier transform of this one is not equal to x of e to the j omega over 2. It is expected that it must be x of e to the j omega over 2, but it's not. And it's a very bad idea to proceed further from here because it's a little bit complicated. It's like we have that component, which is this one, and in order to make everything 2 pi periodic, we just shift this thing by a factor of 2 pi and put further wide triangles around 2 pi, around minus 2 pi, etc. And then it will be 2 pi periodic. So it is not equal to that one, but it is somehow related to x of e to the j omega over 2 plus x of e to the j omega minus 2 pi over 2 as well. Something like that. But it's complicated. And I don't want, again, I don't want to go into the details of this one. By the way, if I'm not sure whether it's an elective course or not, but if you take DSP, Digital Signal Processing, in the 4th year, because when you pass from here this course, in the 4th year you will be eligible for choosing that DSP. A majority of time will be spent on there. How to make downsampling and what is the Fourier transform corresponding to that downsampling, and it's a whole course. So it's difficult. I shouldn't torture you by trying to teach you what a downsampling Fourier transform would look like. It's a little bit tough for this course. So let's leave it with upsampling only. Okay? And let's not go into the details of downsampling. We have other transform properties. We will continue with that, but it's a good time to give a break. So let's stop at this point. We will continue. The quiz will be, okay. The quiz will be in the next hour. Neden diye sorabilirsin. Çünkü ikinci saatte kaçıyorsunuz.